Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Imagine a plastic spoon, a 3D printing filament, a medical suture, or a food packaging film. Now imagine that the starting point of this plastic was not crude oil, but sugar from corn, cassava, sugarcane, or beet. This material is called PLA, Polylactic Acid, also known as polylactide. It looks like ordinary plastic. It can be extruded, injection molded, thermoformed, spun into fibers, and even printed on 3D printers. But chemically, it belongs to a special family of polymers called aliphatic polyesters. The magic of PLA is not only in its renewable raw material. The real engineering story begins in its polymerization technique, how small lactic acid or lactide molecules are converted into long, strong polymer chains. Today we will explore the complete engineering behind PLA polymerization, from history, raw material, fermentation, lactide formation, direct polycondensation, azeotropic polycondensation, solid-state polymerization, and finally the most important commercial method, ring-opening polymerization. Lactic acid was first discovered in sour milk by Scheele in 1780, and industrial lactic acid production developed after fermentation work in the late 19th century. Today, more than 90% of lactic acid is produced through microbial fermentation of carbon sources. PLA stands for polylactic acid. Its repeating unit comes from lactic acid, a molecule with the formula CH3CHOH. COH. This molecule is special because it has two important functional groups. First, a hydroxyl group, OH. Second, a carboxylic acid group, CONH. Because one molecule has both groups, it can react with another lactic acid molecule to form an ester bond. When this reaction repeats thousands of times, we get a polyester chain, PLA. Lactic acid ester bonds long polymer chain PLA is a semi-crystalline thermoplastic. Typical values include a glass transition temperature around 45 to 65 degrees Celsius, melting temperature around 150 to 160 degrees Celsius, density around 1.21 to 1.43 g/cm superscript 3, and Young's modulus roughly 350 to 2,800 MPa, depending on grade, molecular weight, crystallinity, and processing history. This is why PLA is useful but also limited. At room temperature, it is stiff and clear. But near 60 degrees Celsius, it starts losing stiffness because it approaches its glass transition region. That is why a PLA cup may look strong on a table, but fail in a hot car.
The history of PLA is not new. It is almost a century old. In 1932, Wallace Carruthers and his team demonstrated the ring-opening polymerization of lactide. This was a major turning point because direct lactic acid polymerization often produced low molecular weight material. Ring-opening polymerization made it possible to produce higher molecular weight PLA. But there was a problem. Early PLA was expensive, unstable, and difficult to process. It remained mostly a laboratory and medical material. Then, in the late 20th century, industrial biotechnology changed the story. Companies developed large-scale fermentation of sugars into lactic acid, followed by chemical conversion into lactide and finally PLA. In 1992, Cargill successfully applied ring-opening polymerization in industrial PLA production. And today, ring-opening polymerization remains the most widely used industrial route for high molecular weight PLA. Before polymerization begins, we need the monomer. The journey starts with renewable carbohydrate feedstock. Corn, cassava, sugarcane, and beet contain starch or sugar. These carbohydrates are converted into glucose or dextrose. Then microorganisms ferment the sugar into lactic acid. NatureWorks describes the commercial route as plants capture CO2 into long-chain sugar molecules. Milling extracts starch. Enzymes convert glucose to dextrose. Microorganisms ferment dextrose into lactic acid. But lactic acid has one important engineering challenge. It is a chiral molecule. It exists in two mirror image forms, L-lactic acid and D-lactic acid. This matters because the ratio of L and D units controls PLA crystallinity, melting behavior, heat resistance, and mechanical strength. High L content PLA is more crystalline, while mixed D and L forms are more amorphous. Combining PDLA and PLLA creates stereocomplex PLA with higher heat resistance. In polymer engineering, molecular weight is everything. Low molecular weight PLA may be brittle and weak. High molecular weight PLA can be processed into films, fibers, and 3D printing filament. So the central engineering question is, how do we convert lactic acid into long chains without degrading it? PLA is mainly synthesized by two broad routes: polycondensation of lactic acid and ring-opening polymerization of lactide. A review identifies four major practical methods: direct polycondensation, azeotropic polycondensation, solid-state polymerization, and ring-opening polymerization. Now let us understand each technique clearly. Direct polycondensation is the most straightforward method. Lactic acid molecules react with each other. The COOH group of one molecule reacts with the OH group of another. An ester bond forms and water is released. This looks simple, but industrially it is difficult. Why? Because this reaction is an equilibrium reaction. For every ester bond formed, water is produced. If water remains inside the reactor, it pushes the reaction backward and breaks ester bonds by hydrolysis. So to make high molecular weight PLA, water must be continuously removed. The reactor is heated. Vacuum is applied. Sometimes inert gas is used. Catalysts may be added. But as the mixture becomes more viscous, water removal becomes harder. According to a PLA synthesis review, direct polycondensation usually produces low molecular weight PLA, often below 50,000 grams per mole, because of the difficulty in removing byproduct water. So direct polycondensation is simple, but it struggles to produce high-performance PLA. Its advantages include low complexity and potentially lower raw material handling, but it is limited by low molecular weight and high risk of degradation. Azeotropic polycondensation improves direct polycondensation by using a solvent that helps remove water. In this process, lactic acid is polymerized in an organic solvent. The solvent forms an azeotrope with water and carries it out of the reaction system. This shifts the equilibrium forward. Less water means more ester bond formation and higher molecular weight. Azeotropic polycondensation uses suitable solvents to remove water efficiently and allows the reaction temperature to remain lower, reducing side reactions. The solvent is not just a liquid medium. It is a process tool that improves heat transfer, reduces viscosity, and protects the polymer from thermal stress. But this method has its own problems. Solvent recovery is required. Solvent purity must be controlled. Environmental and safety concerns increase. The process becomes more complex. While it offers better water removal and higher molecular weight, the costs of solvent handling and recovery make it less attractive for large-scale production. Solid-state polymerization, or SSP, is a clever method. Instead of trying to build long chains in a viscous melt, engineers first make a lower molecular weight PLA prepolymer. This is then converted into powder or pellets. These solid particles are heated at a temperature above glass transition but below the melting point. A review describes SSP as a two-step process, producing an oligomer at high temperature, then increasing molecular weight in the solid state. This method has one big advantage. The material stays solid. Water and small molecules can diffuse out more easily compared to a thick, viscous melt. The polymer chains slowly react at their ends, increasing molecular weight without severe thermal degradation. Its advantages include improved purity and lower side reactions, though it requires longer residence times and careful control of particle size and crystallinity. SSP is like slow cooking the polymer, gentle, controlled, and useful when purity and molecular weight matter. Now we reach the most important technique, ring opening polymerization, or ROP. This is the dominant industrial route. But before ROP, we need a special cyclic monomer called lactide. It is like two lactic acid units joined into a ring. The commercial sequence involves transforming lactic acid into lactide rings, then opening the ring and linking them into long PLA chains. First, lactic acid is dehydrated and condensed to form low molecular weight oligomers. Water is removed under heat and vacuum. The chain is not yet long enough for final polymer applications. Next, the oligomer undergoes depolymerization through internal transesterification. This step is called backbiting. The chain end attacks the ester linkage inside the chain, forming cyclic lactide molecules. The lactide must be purified because impurities strongly affect molecular weight, color, stability, and final PLA properties. Lactide synthesis and PLA polymerization are usually separated so the lactide can be purified before polymerization. In the polymerization reactor, purified lactide is heated with a catalyst and sometimes an initiator. The ring opens and lactide units add one by one to the growing polymer chain. Simple explanation, a ring becomes a chain. Common catalysts include tin-based catalysts such as stannous octoate, also known as tin-2, 2-ethylhexanoate. Traditional industrial ROP often uses tin-based catalyst systems under controlled heat and low moisture conditions. ROP can produce high molecular weight PLA suitable for industrial processing. It gives better control over molecular weight, stereochemistry, and final material performance. Typical ring opening polymerization requires strict control of moisture, temperature, catalyst concentration, lactide purity, residence time, vacuum or inert atmosphere, mixing efficiency. Why moisture control? Because water acts as an initiator and chain transfer agent. Too much moisture reduces molecular weight. Why temperature control? Because high temperature accelerates polymerization, but excessive temperature can cause degradation, racemization, and backbiting. One exciting engineering method is reactive extrusion. Instead of using only a batch reactor, polymerization can take place inside a twin-screw extruder. The extruder acts as a reactor, mixer, heat exchanger, and material conveyor, all in one. Reactive extrusion can improve mixing, reduce residence time, and allow continuous production. A PLA synthesis review reports that twin-screw reactive extrusion improved conversion yield to 99% and reduced reaction duration to about 7 minutes in one studied method. This is a perfect example of chemical engineering meeting mechanical engineering. The screw profile, barrel temperature, residence time, torque, devolatilization zone, and pelletizing system all decide the final polymer quality. Let us compare the methods simply. Direct polycondensation is a simple route from lactic acid, but water production makes its removal difficult, usually leading to lower molecular weight. Azeotropic polycondensation uses solvents to remove water for better molecular weight, but adds complexity. Solid-state polymerization uses pre-polymer chips under gentler conditions for good purity, but is slower. Ring-opening polymerization uses purified lactide and is the most important commercial method for high molecular weight PLA. In simple words, direct polycondensation is the shortest route. Ring opening is the most powerful, solid-state is a refinement, and azeotropic is solvent-assisted.
In PLA production, lactide purity is not a minor detail. It is one of the most important quality parameters. Impurities such as water, residual lactic acid, mesolactide, catalyst residues, and low boiling compounds can change polymerization behavior. Even small amounts of water can reduce molecular weight. Even small stereochemical changes can change crystallinity. Purity controls molecular weight, color, thermal stability, crystallinity, processing behavior. A PLA plant is not just chemistry. It is a full engineering system. Major equipment includes fermentation tanks, filtration systems, evaporators, distillation columns, prepolymer reactors, lactide reactors, vacuum systems, condensers, crystallizers, ring-opening polymerization reactors, twin-screw extruders, devolatilization units, pelletizers, dryers, nitrogen blanketing systems, quality control laboratories. The most critical engineering controls are low moisture, stable temperature, uniform mixing, efficient vacuum, controlled residence time, catalyst dosing accuracy, devolatilization of residual monomer, final pellet drying. If any of these fail, the final PLA can have poor molecular weight, yellow color, weak mechanical strength, or unstable melt flow index. Once polymerized and pelletized, PLA can be processed like many thermoplastics. It can be used for 3D printing filament, food packaging, disposable cups and trays, fibers and non-wovens, medical sutures, drug delivery systems, agricultural films, consumer goods, automotive interior parts. The Total Energies Corbion PLA plant in Rayong, Thailand, started with a capacity of 75,000 tons per year, producing PLA grades for packaging, consumer goods, 3D printing, fibers, automotive, extrusion, thermoforming, injection molding, and fiber spinning. But PLA is not a perfect replacement for all plastics. Its limitations include low heat resistance in standard grades, brittleness, slow crystallization, moisture sensitivity during processing, limited toughness, need for industrial composting conditions in many cases. That is why PLA is often modified by blending, copolymerization, plasticizers, nucleating agents, fillers, or stereocomplex formation. Polymerization technique controls the base polymer, but modification controls final performance. For example, adding PDLA to PLLA can form stereocomplex crystals. Adding nucleating agents can increase crystallization speed. Blending with PCl can improve flexibility. Adding fibers can improve stiffness. Copolymerization can adjust degradation behavior. PLA's natural limitations include brittleness and limited thermal stability. One review notes that less than 10% elongation at break can limit PLA in applications requiring high plastic deformation. Narrator: so the future of PLA is not only about making PLA. It is about making the right grade of PLA for the right application. PLA polymerization is a beautiful example of modern engineering. It begins with agriculture and fermentation. It passes through purification, dehydration, reaction equilibrium, vacuum technology, catalysis, stereochemistry, and polymer science. It ends as pellets ready for extrusion, injection molding, 3D printing, fibers, or packaging. The entire story can be summarized in one line: sugar becomes lactic acid.
Lactique acide be comme lactide. Lactide be comme plat.
PLA becomes a product. Plant sugar fermentation, lactic acid, lactide, ring opening polymerization, PLA pellets products, direct polycondensation teaches us the difficulty of removing water. Azeotropic polycondensation teaches us the power of solvent-assisted equilibrium control. Solid-state polymerization teaches us the value of gentle chain growth. Ring-opening polymerization teaches us why purified cyclic monomers are the key to high-performance bioplastics. PLA is not just a biodegradable plastic. It is a story of chemistry, biology, mechanical design, heat transfer, vacuum systems, catalysis, and industrial scale-up. And as the world searches for lower carbon materials, PLA stands as one of the most important bridges between renewable feedstocks and modern polymer engineering. From a sugar molecule to a polymer chain, PLA proves that the future of plastics may not begin in an oil well, but in a fermentation tank and a polymerization reactor.